This video is part 2 of 4 in a series that introduces Julia programming language and its application towards linear regression models. In this video, we will continue to learn the basics of Julia language and introduce its application towards simple linear regression models. In statistics, linear regression is the approach towards modeling the linear relationship between a scalar response variable and one or more explanatory variables in a dataset. Simple linear regression models are those which only incorporate one explanatory variable. Here we can see a simple linear model. Our yi represents the scalar response variable, which can be equated with beta 0 plus beta 1 times xi plus epsilon I. Our y will be chosen from our dataset, and we will choose an appropriate variable to be our explanatory x from the same dataset that we believe can explain the outcome of y. For example, if we had a dataset of car models and variables regarding their mileage, fuel efficiency, weight, and other variables, we may want to predict the outcome of miles per gallon using the car's weight to see if there is any correlation. The beta coefficients can be negative or positive and represent the degree of change in the outcome variable y for every 1 unit of change in the predictor variables. This means for every 1 unit our x changes, the y will change by beta 1 units. Thus, beta 1 can be thought of as a slope, while beta 0 is our intercept value. Epsilon I is the independent random error associated with our y. It is expected to be 0. It is important to note, loading data into Julia can be trivial if you are not using the correct package and function, so for now we recommend strictly practicing on datasets saved as CSV files, which can be loaded using the following code. You will first download packages using the package add tool as shown in video 1, and then load the package with the using function followed by the package name. In this case, the CSV package will allow Julia to read in our dataset. Now, let's use Julia to create a simple linear model. The CSV, data frames, GLM, and plots packages will be used for this, and can be downloaded and loaded into your workspace. We will next load our dataset into Julia and name it df, as previously shown. Remember, the path to your CSV file will be different than the one displayed here. The dataset we are using regards the hourly energy output of a power plant, our scalar, and includes over 9,000 data points collected. The set also includes the explanatory variables temperature, pressure, humidity, and exhaust vacuum, which will all be our possible x values. We can use the LM function, which comes from the GLM package, to display a summary of a linear model using whichever x we would like to use as our explanatory variable. Let's try this using temperature. The LM function calculates our beta 0 and beta 1 values using the data for energy output and temperature. If desired, a 95% confidence interval of these estimates can be attained through the confint function as shown. Now, let's create a simple linear model and plot its data points with a line of regression. We can save columns from our dataset as vectors using the following format. This allows us to call upon these variables for later use. These numbers indicate which column our variables appear in the dataset. Here, energy is the 5th column and temperature is the 1st. We will again use temperature as our explanatory variable to predict energy output, our y. We can use the linreg function from GLM to estimate the intercept and slope of our model. Let's name this estimates. We will use this later. We use linreg instead of LM here so that we can save these numerical values as a vector instead of a summary output. We can next use the scatter function from the plots package followed by our newly named x and y vectors to create a scatter plot of our data points for temperature graphed against energy output. Users are allowed to label their scatter plots however they choose. For now, let's label our data points temperature versus energy. If you would like to change the labeling on our x and y axes on the plot, use the following code. To draw in a line of regression, we will use temperature again as our x values, but instead of using energy output as y, we will use our linear model equation to create a linear line through our scatter plot. We will extract our beta coefficients previously saved as estimates and input them into our formula intercept plus slope times x. We will also label this line of regression. This plot indeed shows a linear relationship between temperature and energy output, with a negative slope, our beta 1, which we saw equaled about -2 from our linreg output. We have now learned how to create a simple linear model, how to plot these data points, and how to draw a line of regression through our scatter plot. Now, let's learn how to run a t-test using our temperature variable. A one-sample t-test is used to determine whether a sample of observations could have been generated by a process with a specific mean. The hypothesis tests package in Julia yields the one-sample t-test function, which allows you to perform a two-sided one-sample t-test. Note that since our data was in data frame format, it has to be converted into array format for this function to work. Use the first argument in this function to do so as shown. The second argument for the one-sample t-test function specifies the value of the mean we would like to test for. In this case, we are testing to see if the temperature column of the dataset has a mean value of 19.5. Note that the confidence level is fixed at 0.95, and the test can only be two-sided. There is no option to make it one-sided. Our null hypothesis here is that our sample mean is equal to 19.5. The result of our code shows that we would reject this hypothesis and instead look towards a mean closer to 19.65, or one included in the provided 95% confidence interval. This concludes part 2 of 4 in our series. Video 3 will further our practices of linear regression in Julia, using multiple regression models. We will also learn how to use 3D plots and planes of regression. Video 4 will conclude with different diagnostic tests and more advanced tricks in Julia to make our coding a seamless process. As always, thanks for watching.